This is a lecture primarily for critical thinking class with Dr. McLaughlin, and the topic is, what is science? So what we're doing is we're providing a broad introduction and overview to the concept of science and defining it in a way that we can work with, particularly in this class, but maybe in many other classes as well. Now, there are many different definitions that you'll get, not only in the dictionary, but also in science textbooks and maybe on day one of science class of what science is. And I don't think that there's going to be much disagreement between how I'm going to present things here and what those sources are going to tell you as a definition of science. Really, I think many people see it as the same thing. We're just maybe splitting it up in different ways that sort of make sense to us or how we think it best makes sense to others. But what I think everyone would agree upon is that above all else, it's a way of knowing. It's a way of knowing, especially about the natural world, about nature, about the universe, about life. Now, human and animal behavior, being a part of nature, are studied in psychology. So psychology is the science of human and animal behavior, and so that's why we talk about science and psychology sometimes interchangeably in this class, although of course that's an assumption that we can challenge later on. Is psychology a science? But I'm going to argue that it is, and that it's a way of knowing about human and animal behavior, that particular part of the natural world. So we're a branch of science. And it's a great way of knowing about the natural world for several reasons. It's probably the best way science is for understanding nature for a few reasons. For one thing, even though it can be highly technical and difficult to understand sometimes, it's also a way that we can sort of write down and communicate to each other our understanding about the natural world in a very sort of understandable and coherent kind of way. So one scientist can talk to another scientist in another side of the world, maybe across generations, and still sort of understand things in similar ways. Another really nice thing about it, and why it's also a great way to understand the natural world, is that you can always check. There's an element of seeing is believing. So if you wanted to put in the effort, you could redo the science that's already been done. You can essentially relearn or reestablish a particular fact, or check and make sure that the answers you get match up with the answers somebody else gets. Even something that was done a long time ago, so you can redo studies, and if you want to, see if they still make sense, see if maybe we need to rethink things. So that's a very important part of science as well. Your textbook author, Stanovich, on pages 8 through 13, kind of asks this question: what then is science? And he goes on to identify 3 key things in chapter 1 that really science has to feature, or 3 important features that science has that are very, very helpful. And again, it might be different from how you've seen things presented before. It's certainly different from how I used to talk about science and the scientific method. But I think this really covers a lot of the important features and the benefits of thinking scientifically. So we're going to go through these things step by step: systematic empiricism, publicly verifiable knowledge, and lastly, empirically solvable problems. So the first thing he talks about is systematic empiricism. I should note that all 3 of these are pretty interrelated in a lot of ways, so you'll hear themes that are repeated, and as we go through the course, even when I'm not speaking about science directly or defining it as I am right here, you're going to hear a lot of these same topics and points being made. So systematic empiricism, what I'm actually going to do is I'm going to define that, but I'm going to define the second term first: empiricism. So what empiricism basically is the idea that we learn using our senses. That's really all it is, and it doesn't seem that earth-shattering, but we contrast that with rationalism, with the idea that a great way to learn about things is to make arguments, to think things through. And that's an important conversation and debate that we're still having. To what extent do we need to just think things through and think about, here's what makes sense, here's the way things should be, and to what extent do we kind of say, well, I'm not sure about this, but I'm going to go look it up. I'm going to go look in the real world. I'm going to make observations. That's being empirical, basically. And as we might have been talking about already, there's a little bit of humility in the empirical argument. It's this idea that I'm not necessarily going to come up with this great argument or this really rational line of thought, or through my impeccable logic I'm going to improve things. Instead, I'm going to say, you know, I don't know, and I'm going to go find out. And not only that, everything that I hold to be true is kind of tentative. So I'm not 100% sure because things can change. And if I find things out, I do so empirically. I make observations of the world. I conduct experiments and studies. And I might get a particular kind of results, and that leads me to think one way, but then later on in the future, maybe 30 years down the road, if I get a very different set of results, I go, you know what? I was wrong. And empiricism as sort of a branch of philosophy, this idea that there is no innate knowledge, there's no set of rules that we have to follow, and really we learn everything through our senses. There are a lot of philosophers who really push that perspective, particularly John Locke, the English philosopher, who said, in this quote, "Whatever I write, as soon as I discover it not to be true, my hand shall be the forwardest to throw it into the fire." The forwardest, not a word that we use too much anymore. But in other words, this idea that anything that I declare to be true, if I find out later on it's wrong, I'm going to say it's wrong, and I'll be the first one to do that. So there's a little bit of that humility, because you have to once in a while say, you know, I used to think this, but then evidence changed my mind. And when I say that, it's not that there's no place for rationalism, for making good arguments or using logic, but psychological questions, some really important ones, like for instance, you know, from all areas of psychology, everything to what are good qualities of a leader, to what causes mental illness. That can lead to a lot of great reasoning and thinking and speculation as to why that is. But we believe our observation above all else. Why? Because many well-reasoned ideas, many brilliant lines of reasoning and logic have turned out to be wrong. Reasoning can help us decide what to study, but then we have to listen to the answers that our senses are telling us. So for instance, a person might be of the belief that maybe mental illness comes from, or schizophrenia to be more specific, just to choose one example, comes from some very early life experience. Or maybe it comes from some events that happen, or an illness that the mother has while the child is in utero. Now that's an interesting argument. And we can come up with logic and reasons why that might be true, and it's interesting, but still then what we have to do is go and see, well, if that fact were true, if this idea or concept is true, what kinds of things should we see in the world? So that term see, meaning we're going to make observations to verify that our ideas are true. And then if it turns out that no, there doesn't seem to be any relationship between early life experience or in utero experiences or illnesses and the development of mental illness, then we have to say, kind of like Locke did, be the forwardist to say, well, our idea was wrong. So being empirical means we do this. We say that observations that we make are greater than arguments that we make. So arguments, lines of reasoning, that's great. And it can help us determine what to study, but really observations are key. Making observations, doing studies and saying, I don't know, but I'm going to go find out, and what I find out is going to inform my opinion. It's going to change what I believe. In other words, I'm not going to let the facts dictate what I'm not going to allow what I believe to be true to dictate the facts that I look at. Rather, I'm going to use facts as I observe them to help dictate what it is I hold to be true. So that's empiricism, this belief that I'm going to make observations using my senses, and that will help me determine what I think is real and not real. But we say systematic, so that's the other part of this. Because empiricism in and of itself, you know, philosophically, you can picture someone who just kind of observes everything, who senses, who looks and listens. And it can be hard to tell, well, how do I turn that into a belief? What kinds of ways of learning about things and observing the world are better than others? So here's where we can be rational and kind of say, okay, I have an idea in mind, and I'm going to spell out ahead of time. I'm going to make what we call a hypothesis, and I'm going to spell out ahead of time, here's what I think I should observe. And I'm going to do it in that step-by-step fashion, where I'm going to come up with an idea. I'm going to decide, here are the observations that would agree with that idea, and here are some observations I might see that would disagree with that idea and might tell me that, no, that idea is wrong. And then I'm going to go test them. And then based on the results of that test, I'm going to modify my idea, my hypothesis. I'm going to change it. I'm either going to go, yeah, it was right, or I'm going to go, nah, it really didn't work out. So that's the systematic aspect of it. So this is really important in psychology because people are different. There are some other fields of science where it's very, very easy to just kind of make a simple observation and it very quickly proves or disproves things. In psychology, we have this understanding that people are different, and what works for one person might not work for another. So we have to be very, very careful of just saying, well, I made an observation and I looked at my friends and here's what my friends are like, therefore it's a universal truth in psychology. We really can't do that. So there are certain rules and ways of kind of understanding human nature and human behavior that we have to follow. Simply finding one or two cases, what we call the person who or testimonial evidence kind of thing, isn't good enough. So our empiricism should be guided and follow a step-by-step procedure. So that's what we mean by systematic empiricism. Observing the world in a step-by-step, spelled-out, methodological kind of a way. Second thing, it's another very important feature of science that helps us have confidence in the things that we learn. And it also helps those who are not scientists, like many of you might not be, sort of have confidence in the knowledge that scientists are providing, people who typically do a lot of scientific research, that you can understand it, that it's publicly available and verifiable. In other words, we can make sure, there are ways to make sure that what we're saying is true. You don't have to take people's word for it if you don't want to. Now, very often you will, because you're not going to assume people are lying, but the idea is you can ask people, show me the evidence, and they should be able to. So for one thing, people who do the studies communicate what they find to the public and, very importantly, to each other. Now, this can be in publications like the articles we've looked at or might be looking at, or from people who give talks or go to research posters like the research posters you see on campus, where people will stand in front of that poster at a conference. Like, you can picture a very large arena, like a really large room, and just rows and rows of these posters, and you can go there and you can stand right next to somebody as they kind of talk you through the results of their study and how they did everything, and you can test them if you want to. You can ask them, really challenging questions. Be nice, but that's what they're there for. Scientists and institutions also make knowledge available on their websites by giving lectures, giving workshops, and other ways. Also, scientists learn about what other scientists do that way. So it's important for the public to check in on this stuff and understand it, but sometimes if you're not, an expert in a particular field, it can be hard to know the questions to ask or the things to spot that make you kind of say, I don't really trust what this person is telling me. Now, of course, a huge part of the critical thinking class is to talk about exactly that. How do we know and what things should we look for? But it also makes it important for scientists to check on each other and to be able to find ways to challenge each other and kind of say, well, what you found is different from what I found or different from what somebody else found, another paper that I've read, and we can talk about why that is. So that's another important thing as well, is that science is self-correcting. There are ways to do that. It's not just once something is declared and put into a textbook, it's true forever and all time. People can challenge these ideas, and they can do that by replicating each other's studies. In other words, if there's an interesting study out there, and if I have a question about it, or I'm not sure if it came to the right conclusion, I can redo it. I can redo it either because I'm trying to prove that it does work and it is a good idea and it is a good conclusion, or that the scientific study had a good conclusion, that's a fact. Or if I'm trying to challenge it and say, I don't think I would get that if I were to redo that study right now. You should be able to do that. And so that's part of why in psychology articles and in science articles in general, there's a very detailed step-by-step method section. There's a recipe that allows you to do basically what a recipe is supposed to do. You're writing down the instructions. Here's how you would redo the study if you decided to replicate it. It also allows us to be open and check on each other and say, I don't like the way you did that study. I don't like the way you defined these variables, or I don't like where you got your research participants from, or I don't like the analysis that you conducted. You can do that by reading somebody else's method section. And if you really think it's that big of a deal and you've got the resources to do it, you can redo the study and see what you would find. Another important thing is by peer review. The publications, the scientific journal articles that we'll be looking at, the conferences that scientists go to where they present their research, their research studies are peer reviewed. In other words, if I'm going to go and publish an article, what I actually have to do is I'll send it to the editor of a journal, and the editor makes a decision, does she or he want to publish my article or not? And the way that that person makes that decision is by sending it out to a few, usually between 2 and 4 peer reviewers. Other people in my field who do similar research to me, and they're going to anonymously critique my research, and usually they're going to deliver a judgment, which is, I recommend that you publish this article, or I recommend that you publish this article only after this person takes care of these huge issues in their article, or sometimes I recommend you reject this study. So peer review is a really, really good process because it allows people who read scientific research to be safe and confident that whatever it is you're reading has already passed a test of other scientists, other people knowledgeable in the field. And I can tell you for a fact, people can be extremely critical. Every scientist has tales of research, success stories, research they've had that has been published and everything went great, but also failures. Research that they've sent away for publication, and reviewers just tore it apart and said this isn't very good. So that means that anything you're seeing, anything that you see in a scientific journal or at conferences was good enough to pass that test. So that's why you can be at least a little bit more confident in scientific literature, in the publicly verifiable knowledge that science provides, versus things you see on websites where you have no idea if that information was vetted at all. It could just be something that somebody wrote, a bunch of other people like it, and they share it, but it could be completely false. And nobody really checks on these things, and people are under no compulsion to take things down just because somebody else points out, hey, what you're saying is completely not true. In a peer-reviewed journal article, that's exactly what happens. And in fact, sometimes if it turns out later on there was a grievous mistake or error in the scientific knowledge, the journal will actually retract the study and publicly say, we're retracting this because there were problems with the research study. So science is always self-correcting, and that's really, really good. We expose our flaws and mistakes, and sometimes that can make us look bad and be really embarrassing, but in a lot of other forms of knowledge and a lot of other places where you get knowledge, there's no mechanism for doing that and for making sure that what you said is correct is still correct, and everybody still thinks so. Lastly, science is all about examining solvable problems. Now, not all problems are solvable. And one of the things that your textbook points out is that you can make a distinction, or at least one person does, between what are called problems and mysteries. Problems implying that it might be a very, very difficult one, but at least maybe there's some kind of solution. So curing disease, things like that, as opposed to mysteries, which are sort of these questions that are very, very important, but are probably never going to be solved. So some examples are, what is the meaning of life? Now that's essentially too big a question to answer scientifically. It doesn't lead itself to be studied in sort of that methodical kind of step-by-step empirical sort of way. You wouldn't even necessarily know if you're trying to answer a question like, what is the meaning of life? How do you even know that you've made progress answering that question, or that you're getting close to a correct solution? It's not really a scientific question. It's not a solvable problem, exactly, by most people's reckoning. Now, it could be informed by science, so we could look, for instance, at the research on positive psychology to get a sense of what makes a happy and fulfilled life. So aspects of science or things we gain through the scientific method could help us answer those questions. But really what science is restricted to is solvable problems. Now here's how that works. Now this is going to be a detailed account sort of what the scientific method actually is and how it operates. And again, it might be different from how other classes have presented it, and this is just one way of doing things, but I think this way really works. So what I'm going to present for you is kind of a wheel, because what happens is, as we learn things, they change what we already believe to be true, and that changes how we look at things. So it's this back and forth between going and making observations in the world and then changing what our thoughts are, and that changes how we observe the world. So 3 things. Let's start with a hypothesis. A hypothesis is an idea. It's an idea that we've got in minds, not something that we necessarily believe is true, but something that we believe could be true. So we might have already defined the idea of tolerating ambiguity, this idea that I can hold an idea in mind and not believe it and not disbelieve it. It's something that may be true, I just haven't seen enough evidence for it yet. Now, a key aspect of this hypothesis is that it must be what we call falsifiable. Here is a term that we're going to be using over and over again. Hypotheses must be falsifiable. In order for them to be scientific ideas, we have to be able to, in theory, prove them wrong. There has to be an idea or a condition where they can be proven wrong. Even if we wanted to do a simple scientific study on, let's say that we think that exercise helps improve people's mood. Well, we could conduct a study. That's our hypothesis. Exercise will improve people's mood. And if we go and make our observations and do our study, what we're going to be doing is we're going to be going to the next step of this wheel and actually testing our ideas. We're going to go out and make those empirical observations. What we might find out is when we have people exercise, their mood improves. In which case, that's evidence in favor of our hypothesis. Or our hypothesis might be falsified. We could find out that no matter how much you have people exercise, it really doesn't seem to change their mood that much. Now, I'm not saying that's the truth. It turns out there are a bunch of studies that suggest that there are a lot of psychological benefits to exercise. But in other words, there is a way, according to our hypothesis, that we could be proven wrong. That's really key. If in our hypothesis there's no situation or no observation we could possibly make that would prove our idea wrong, then our idea is not a scientific one. That's the important distinction. So if we decide in a question, in this question of what is the meaning of life, if we decide that the meaning of life is for people to be happy, how would we test that? That'd be really, really challenging to try and disprove that. So it's not really a falsifiable question. Science answers falsifiable questions. There is a possible way, there is a possible outcome where we can go, yeah, okay, our idea was wrong. So all hypotheses have to be phrased in such a way that they could be proven wrong. Not that they are. Sometimes there's confusion about this. I ask people, is this idea falsifiable? And sometimes they tell me, yes, it's falsifiable because it's wrong. That's not really what I mean. Everything that you've read in a textbook and everything that a psychologist or a scientist has said, here is something that is generally believed to be true, that's a falsifiable idea. So we conduct our test, and our test changes a theory. A theory is larger than a hypothesis. It's a large set of ideas or one explanation that ties together a bunch of different observations. Now, a theory, I would argue, really can't be proven or disproven by any one fact, by any one finding. Theories are too large. For instance, gravity is a theory. It's just something that we've made so many observations with over time that there's no one thing that would really by itself disprove it. On the other hand, if you do test after test after test, if you do study after study after study, and it seems like your theory doesn't really hold up, your theory doesn't make much sense, your theory is not doing what you would predict that it would do, then your theory goes away. Eventually it dies off. And your theory, another thing about scientific theory is that they generate the testable hypothesis. So a theory is not how we use it in common language, which is just a theory that's like an opinion. That's not what a scientific theory is. A scientific theory generates testable hypotheses. So oftentimes a hypothesis is going to be phrased as, if this theory is true, here's what we should see. Now, a hypothesis doesn't have to be phrased like that, but many of the ideas that we challenge and the things that we test and the research that we do has that in mind. I have this overall theory on the way people are, and where maybe an aspect of our personality comes from, or a theory on the way attention or memory works. Now, nobody has literally observed attention and memory, really. You know, they're kind of theoretical. They're what we call constructs. They're psychological concepts that most people agree exist and that you can study them, but you use them to generate a hypothesis. So this theory of the way memory works, we say, if memory works like this, here's what I should see in a study. That right there is a falsifiable hypothesis. So scientific theories generate falsifiable hypotheses or predictions. And then we use those falsifiable hypotheses or predictions to direct our test, our observation. How are we going to prove or disprove this hypothesis? And then based on the results of that test, we modify our theory. So that's the wheel. That's the back and forth. So this is basically what science is. Again, science is not the only way of understanding the world, but it's an outstanding way, again, for understanding how the natural world works. And over time, psychology has gone from basically just sort of reasoning through ideas about why are people the way they are, what we call the armchair philosophy, to things that are much more active. Let's go find out. Let's have laboratories and let's test people and let's see the way people are and how they tick. And then let's use those results to change theories about the way people are, how to make people happier and healthier. And then those theories create testable hypotheses. And sometimes those theories are gone now. Things we used to believe to be true turned out not to hold up to systematic empiricism. But some of the ideas that we've held on to did sort of fulfill those tests. Tentatively. Again, science changes. That's one of the great things about it. So that's the end of the lecture, and I'll see you in class.